Hi everyone, thank you for joining today's webinar. This is Talia from Unbound Tech. Today's webinar is titled Digital Transformation Best Practices for Cryptographic Key Management and Protection, presented to you by Dr. Yehuda Lindell. He's Unbound's Chief Scientist and co-founder. Today's webinar is about best practices for cryptographic key management. We'll be answering the question, how can organizations protect and control their keys in today's increasingly complex, open, and interconnected IT environment? In today's webinar, you'll learn about how digital transformation is changing key management and protection requirements, what key management and protection methods are available today, and key management best practices for financial institutions, including practical examples. If you didn't already know, Unbound Tech, formerly known as Dyadic Security, was brought to life by the sophisticated applications of multi-party computation, otherwise known as MPC, developed by our co-founders, Professor Lindell and Professor Smart, who are world-renowned cryptographers. MPC offers a mathematical guarantee of security that allows Unbound to protect digital secrets beyond physical boundaries. For the first time, cryptographic keys or any other digital secret are never exposed throughout their life cycle, from edge to cloud and anywhere in between, without any reliance on dedicated hardware, making crypto easy, user-friendly, cost-effective, and more secure. Some of the world's most successful Fortune 500 enterprises with the highest security and privacy requirements turn to Unbound for its breakthrough solutions. At the end of the webinar, you'll have an opportunity to ask questions, so feel free to send your questions in via the chat box. I'm going to turn it over to Yehuda. Thank you so much again for your time today.
Okay, thank you very much. Okay, today, thank you for joining me. I'm going to talk about key protection mechanisms and best practices and use cases. I'll start by outlining the reason why we have this burning need today due to the digital transformation that we all know is undergoing. I'll discuss the traditional technologies and solutions that have existed and emerging and new solutions. And then I'll go through some best practices and use cases. So we're all familiar and very aware of the digital transformation. Everything is now a computer, whether it be our phone, our car, our fridge, our washing machine even. Our traditional data centers at work are disappearing, or at least they're changing rapidly. We're in the cloud and in data centers, we're deploying across the world. And all of these changes need to be addressed, both from a functional and usability perspective, but also from a security perspective. How do we secure this rapidly transforming and changing world? Cryptography is one of the fundamental tools that we have to provide security. It's not the only tool, it's not the only layer of security, but it is one of the core technologies that we have to deploy. And cryptography enables us to protect data wherever it may be. So it's perfectly suited and much more needed in today's transformed world. So it used to be the case that we had a data center. Inside the data center, we pretty much felt that we could keep our data safe. I'm not sure if that was actually true, but in the past 5 to 10 years, we know for sure that it's not true. Data centers are being breached, secrets are being stolen, whether it be trade secrets, client information, authentication data. These are all being stolen and sold on the open market. Attackers today are much more sophisticated than they used to be, so we need proven, strong solutions to protect our data. Whether it's in the data center or in the cloud by encryption, whether it be authentication via on endpoint devices, digital signatures, whether it be to secure new technologies like cryptocurrencies, or even just providing strong security for classic bank transactions, secure trading, and so on and so forth. All of these require cryptography at the core. Cryptography has been around for a long time, actually way before the 1970s, but let's say that modern cryptography is born in the 1970s with the deployment of open solutions. So encryption schemes that are known and standardized, whether it be symmetric or asymmetric, followed up by the deployment of hardware solutions that could protect the keys used in those cryptographic solutions, and then the widespread use of advanced cryptographic protocols for protecting data in motion. In fact, until 10 or so years ago, the vast majority of the use of cryptography was for protecting data in motion. Again, because of what I mentioned, that inside our data centers, we felt that we could keep our data safe. We know that's no longer the case, so we have to deal with data at rest, and we also actually have to deal with protecting data and other secrets while they're in these flexible environments that are due to digital transformation that I just discussed beforehand. So today we're moving into a new era of what we call software-defined cryptography. Essentially, we need cryptographic solutions that provide a strong level of protection like always before, but when we can no longer be bound to classical hardware solutions that don't suit modern computing environments, whether they be virtualization inside our data center or cloud environments, or even end-user mobiles as places that we want to carry out cryptographic operations. One of the main drivers for change is, of course, usability. We need to be able to rapidly deploy new solutions. Users are not willing to pay the price of having a very strong and very secure solution, but that is not usable, is not easy for them to access, requires them to take hardware with them, or limits their operations, or requires them to input numerous passwords. These are just not viable for the modern environment, and we somehow seem to get into this situation where we're always compromising between security and usability, and we often within our organization will have a lot of tension between the business units and the security groups about how we're going to come up with a solution that meets everybody's needs. That's on the one side of the user. There's also a lot of new challenges and usability, which isn't about the end user, but about our administrators. When we want to go to the cloud, we need to be flexible. How can we administer all of these solutions in this modern environment and still be secure? When we talk about security, a very famous principle that I'm sure a lot of us are familiar with is called Kirchhoff's principle, and that says that our cryptographic systems should be secure or must be secure even if everything is known except for the secret key. So the key is the primary fact that provides our security, and everything else is public knowledge. The fact that everything else is public knowledge is necessary because eventually things leak, but not just that, we need standardized and validated solutions. When someone comes and says, yes, I have my proprietary scheme that I'm not willing to tell you about, the first thing that you do is show them the door. We actually want to know exactly what's inside the solution, and we want it to be standardized and certified. But that means that truly all the security is inside the key, which is fine unless that key is not well protected. Because once the attacker gets the key, everything is lost and your entire solution is completely broken. Security is completely bypassed. So how do we protect those keys, which are the core of the entire security of the solution, in these modern environments where we don't have control anymore over where our software is deployed? We don't have a clear perimeter that we have where we have protection, and we have BYOD devices that are not secure, and all this has to come together and somehow give a good level of security, because attackers today are even more sophisticated and more motivated than ever before. Organized crime is very into the cyber cybercrime area, and we have to provide good protections against all of these scenarios. So this brings us to the necessity for very strong and flexible key management and protection solutions. And the basic requirement is just preventing an attacker from stealing secrets and keys. And when I say a key, I want to stress that I'm really referring to anything that you're doing which relates to secrets. So these can be classic encryption keys, they can be signing keys, they can be authentication information for user login, could be biometrics, it could be the keys that are used to protect SSL sessions, really can be absolutely anything. And the primary goal is to prevent these from being stolen. I'll actually come back to this later on and show that there are other concerns as well, like misusage, but let's get to that later on. One of the problems that arise when talking about key protection or security in general is whether or not we have a clear understanding and guarantee provided by our solution, or in what we call a cat and mouse game. In a cat and mouse game, we provide a solution. The solution is makes it hard for the attacker to somehow get to the secret keys, but not impossible, of course. Well, there's no perfect security ever. Then the attacker tries to break the scheme. They find a vulnerability, they break it, we fix it, and we start all over again. This cycle is one that is very, very problematic from any basic security perspective. We don't have any clear guarantees. We can't really know when the attackers are going to breach our systems. We're constantly under this threat, and what we really need are solutions that provide us much clearer guarantees. And I want to stress that a clear guarantee doesn't mean foolproof security. If anybody tells you to have a 100% foolproof secure solution, then once again, you know that either they don't understand the solution themselves or they're lying. But we can come up with very clear guarantees about what the attacker needs to do to get material, to get the secrets. And if we have that clear understanding, we can build a much cleaner threat model and build our security on top of that. The two main directions or bases for solutions for key protection are hardware and software. And as we'll discuss now, as we present these different solutions of hardware and software and actually what's in between, we'll see some interesting trade-offs between these two directions. The traditional method, and going back many, many years, for protecting keys is in dedicated cryptographic hardware, what we call HSMs or hardware security modules, smart cards, tokens, and so on and so forth. These are dedicated devices that are built to only carry out cryptographic operations. They typically have they come with physical security as well. So even if you have physical access to one of these boxes, you shouldn't be able to get the keys out. This hardware will only provide well-defined cryptographic operations. So you can't ask it to export the key. You can't run any other code inside, so you can't somehow find vulnerabilities to extract keys. And they also have undergone a very rigorous certification procedure, so we have good confidence in the security. It's not perfect, and I'll talk about that also later on, but these devices actually are built for security, and we have good confidence in them. The main problem and drawback of dedicated cryptographic hardware is agility. Hardware, by its name, is hard. It's not something that can be updated in an easy and flexible way. It may actually be the case that vulnerabilities in dedicated cryptographic hardware come up very infrequently, and they don't happen very often. But when they do, the cost of fixing them is enormous. Let's take the recent rocker attack on Infineon smart card chips. There are millions of these chips around the world, and it was discovered that all of the RSA keys generated by these devices can be broken in very, very reasonable time. Now, a smart card can be replaced, but the cost is very, very high. You actually have to physically get the card back from the user, deploy them a new card. That comes with actual, a very high expense. It's also a big hassle for the users and for the organizations, but in some cases it's even harder than that. What do you do about TPMs that are embedded in computers all over the world that you can't just easily swap out the chip? It's not even clear that in all of those chips you can even do a firmware update. In fact, in many cases, it's just impossible to fix the problem. In the SafeNet HSMs in 2015, there was a PKCS11 vulnerability discovery, which actually enabled extraction of keys. So despite all the heavy certification, there was a bug. Now, we know that bugs are an inevitable part of computing, so I'm not saying that it's outrageous that they had a bug. Everybody has bugs. The question is, what's the cost involved in fixing those bugs? So we all work as hard as possible to make sure that our solutions are secure and we don't have any vulnerabilities. But we need to think ahead of time, are we buying a solution that enables us to fix that vulnerability easily, or we're buying something that it's actually very, very hard? And the trade-off is very simple. If I have a solution where the chance of vulnerability is lower, but the cost is much, much, much higher, then my overall expected cost actually goes up. So we need to consider this agility issue very much when buying any solution. And this is really one of the biggest drawbacks of dedicated cryptographic hardware. There are other challenges as well, not on the security side, but on the management and user experience side. Of course, these different solutions don't interact with each other. If I have a mobile or endpoint solution, like you have a smart card for users, this is completely separated from an HSM solution. But even if I have different business units who need to access different sets of keys, very often I need different sets of HSMs for each of those solutions, making the entire operation very expensive and also very difficult to manage. So cryptographic hardware has good security, not perfect, of course, but it also has a significant cost involved and a significant threat involved due to the lack of agility, and we have seen vulnerabilities. But mainly, it's not really suitable for modern computing environments. When we need to go to the cloud and we need to be agile for end users, then hardware just doesn't work. On the other end of the spectrum, we have pure software solutions in software tokens and vaults. These are solutions where different techniques are used to make it hard for the attacker to get inside the software and steal the secret keys that are used in the software. So I want to encrypt or decrypt or sign. If an attacker gets the key, then I've lost everything. So we somehow try and make it hard for the attacker using a series of techniques of obfuscation, encryption, white box crypto, server hardening. And all of these make it just hard to deploy malware or get to that, to get inside the application and steal the secret key. The problem with these solutions is that they just don't work. They're just blatantly insecure. If I want to use encryption, well, it's a chicken and egg problem, right? I want to protect my key by using encryption, but encryption uses the key. So how do I protect the key that I use to encrypt the key? I'm back to exactly the same place I was beforehand. Obfuscation has been used for DRM. It's typically used for DRM, mainly because we don't really have any better alternative, but it doesn't provide long-term security, and it's not something that we want for protecting financial transactions and high-stakes secrets. White box cryptography is a type of obfuscation that's specifically designed for protecting cryptographic secrets, so it may seem attractive, but the bottom line is that it's completely broken. In fact, last year, CHESS, which is the primary cryptography conference on hardware security and things like protecting keys, ran a competition about white box crypto, and there were actually 94 submissions to the competition from the best groups in academia and industry deploying and constructing white box crypto solutions. And within a couple of weeks, all of them were broken. In fact, I think only 2 of them survived more than a few days. So white box crypto is just completely broken, and there are very strong techniques, general techniques, which break them, and these just do not provide reasonable security. And even if I could do this, I still haven't prevented someone just taking that software and going somewhere else, and they can run that software, and they have now a running clone that they can do everything that the legitimate user can do. So these just are very attractive and appealing from a usability perspective, but they don't come close to what we need for security. So we talked about dedicated hardware, we talked about pure software. What about something in the middle? And that's what we have actually. It's also something which is quite an emerging technology, and these are trusted execution environments. We know about Intel SGX, ARM Trust Zone, AMD SEV. These are hardware solutions that provide an environment that you can run whatever code that you want in a protected way. So I design code that I want to be protected. It runs inside this enclave, and protection is actually provided by the chip itself. I can even use an attestation to make sure that I'm running the correct hardware. So you can't, the correct software. So you can't replace out my software with something which is doing something that it shouldn't. This can be used for protecting keys. I can actually build this like a software hardware hybrid HSM by running all my cryptographic operations inside the trusted execution environment. And now I'm getting sort of the best of both worlds, it seems. On the one hand, I have protection provided in hardware by the chip manufacturer. On the other hand, I'm not bound to a physical box. I can possibly go to the cloud if I may have these trusted execution environments also on my mobile. And so I'm getting essentially the advantages of software, but actually with hardware protection. This is what we would have liked to happen, but unfortunately, none of the trusted execution environments actually give me that guarantee. And the reason is that the manufacturers all built these environments in a way that they're not fully isolated from the standard, from the regular computing environment. And what that means is that even though I'm running code in this enclave, which is supposed to be protected, there are shared resources between that protected code and the regular code. And when you have shared resources, then things leak. So we have things called software side channel attacks that can be carried out when you have two pieces of software sharing the same resource, even if the attack software can't look inside the victim software at all. And I'll give you an example. A cache attack is an attack where, since both of these pieces of code running use the same cache, then just by looking at what's in the cache, I can see what the other piece of code is doing. It might sound very strange, but it's extremely effective. And it's been used to actually extract full key material from inside a trusted execution environments like SGX, from cloud environments when you have different VMs running on the same machine, even with the hypervisor being fully protected and there's no breach between the VMs, you're able to use these co-location and side channel attacks to actually extract full information. We all heard about Meltdown and Spectre and speculative execution attacks. The same thing happens here. This interaction between these different pieces of software running on today's extremely complex hardware means that without full isolation, you don't have the guarantee of that we got from dedicated cryptographic hardware. So again, it sounded good. It sounded like this is the same as the dedicated crypto hardware, but there's a fundamental difference because dedicated cryptographic hardware is exactly that. It's dedicated. It means that nothing else runs there, so nothing is going to leak, whereas trusted execution environments just don't fulfill that promise. And it's unfortunate, but I think it'll take years until the chip manufacturers come back with fully isolated trusted execution environments. It'll be a much more expensive chip, but it's possible. And when that happens, then I think that these types of solutions will actually be very, very attractive. But for now, they're just not secure enough. And there's actually a long series of papers demonstrating extracting RSA keys, elliptic curve keys, AES keys, and so on and so forth, very quickly and very effectively from trusted execution environments in very real-world scenarios. beyond the security concern, which is what I discussed now, we also have to note that the argument that on the one hand they're like dedicated hardware, that's wrong because of the security perspective. On the other hand, that they're like software and they can easily be deployed, that's also actually not true. Because it's true that the software that I write to run inside an enclave has agility. I can replace that out. But the security of the enclave itself is not agile. And that's what we saw again with Spectre and Meltdown, and the difficulty in updating and fixing this that Intel and others have been having. Also, you don't have full flexibility to deploy everywhere because not everywhere has access to a trusted execution environment. Not all clouds have, not all endpoints have, and also endpoints are very diverse. So some mobiles have better and some have worse, and that's a very big problem. Finally, as with dedicated hardware, if there is a vulnerability, or maybe when there is a vulnerability, it's very, very hard and expensive to overcome. Again, making this a less attractive solution. So what else do we have out there? There's actually a new technology which is emerging as a practical technology, but it's actually been around in academia for 30 years now. So it was invented in the 1980s, and it's a way of computing on information without ever bringing it together. So in a segregated manner. It's called multi-party computation, or MPC, and it provides mathematically proven security guarantees. As I mentioned, it's been around about 30 years, but for about 20 of those 30 years, it was purely theoretical research. And in the last 5 to 10 years, it's become practical enough for deployment in practice, and that's what I want to present to you now. So it's a pure software approach, so it has all the advantages and flexibility of software, and the way that you can use it to get key protection is instead of putting a key in one place where it can be stolen, you split the key into multiple pieces. Let's talk about 2 pieces for now. So you split the key into 2 different pieces, but each piece is completely random by itself. So if you just see that one piece, you actually can learn nothing at all about the entire key. You have to get all of the pieces at the same time to learn anything about the secret key. And you place these random shares of the key in different places with strong separation or segregation between them. They can be different servers or endpoint, a mobile on a server, or anything that you want. And when you want to perform the cryptographic operation, you don't actually bring the key together. You actually compute it while it remains separate. That's exactly what MPC does, again, with a mathematically proven guarantee. Even if an attacker breaches one of the machines and can run malicious code and interact with the other machine, they cannot learn anything whatsoever about the secret key. In order to compromise the system, they have to breach both of the machines at the same time. This is what I mean by a clear security guarantee. That's what we have with dedicated hardware, unless a vulnerability is found inside the hardware, like has happened with Rocker, for example. But unless that happens, we have a very strong guarantee about the security of the hardware. With software and with trusted execution environments, we don't have that because these are inherently vulnerable type solutions. And with MPC, we have a clear guarantee that unless the attacker gets to both machines at the same time, they won't learn anything about the key. Of course, how hard it is for the attacker to get to both machines at the same time, that's something that depends on the deployment, and that will also influence the security of the solution a lot. Once we have MPC and we have efficient solutions for deploying key protection via multi-party computation, we can now enjoy the full flexibility of software. So we can split keys between any types of environments that we like. We can talk about cloud environments where I may want to keep one part of the key in my data center, in my organization, and the other part in the cloud. And this is what we would call control your own key, which is very different from bring your own key. When people say bring your own key, I don't really get what I'm gaining, because I bring the key and then I give it to the cloud provider. Now they have the key. So what difference does it make if I brought it or they generated it? They have the key, and therefore I'm relying fully on them for my security. With an MPC type solution, we can separate the key between the organization and the cloud, and now each of those environments are secure within themselves, and there's very strong separation between them. We can also go across different clouds or different regions or different parts of the world, and that's something that we can get using MPC. We can deploy advanced authorization schemes, which I'll discuss later on. And we can also protect general secrets and not just classic cryptographic keys, because MPC can handle also biometric authentication and more while protecting and having this separation. It's really crucial to understand, though, the security of an MPC-based solution depends on the ability to get strong segregation. So you think about having different administrators on different machines, or at least different credentials, where one of those sets of credentials is offline and not used for anything else. It's also not needed to administer the system, so that's okay. We can have different machine types, different operating systems, different environments, different physical locations, and so on and so forth. The stronger the segregation, the better security that you get. If you think about a mobile and a server in the organization, you have very, very strong built-in segregation. Likewise, between a data center and a cloud, within a single data center, you can also get very strong segregation. Then you have to think about different credentials or operating systems, or at least something like that. In this table here, you can see a summary of these different solution approaches and what they give you. The dedicated hardware excels when it comes to security, and that's great. Unfortunately, in modern computing environments, when we need usability, it performs very, very poorly. However, it's also not all that clean on the security side because of what we discussed with agility and the problem of what to do if a vulnerability is discovered. And there's also an issue of key usage, which actually doesn't deal with it all. Software tokens, on the other hand, are fantastic when it comes to usability, but I really don't think they're viable for any financial institution because they just don't provide a good enough level of security. It's not something that I think that we can rely on to protect valuable assets. Trusted execution environments should have been the ultimate solution to our problems, had the manufacturers built in strong isolation. I guess when they planned these solutions, they weren't aware of these software side channel attacks. In fact, they were only discovered recently, over the last 5 years or so, by the security researchers. So it's not an issue of blame, it's just an unfortunate situation where we had something that really could have solved our problems, and in the end doesn't provide us strong enough security guarantees and is not as usable and flexible as we would want it to be. Finally, multi-party computation has the potential to provide a very good trade-off between giving us very strong security, again on the assumption that you can deploy good segregation. If your environment is one where you can't get any segregation, then I don't think MPC is going to be the way to go. But in large organizations, segregation is always possible to do. And in modern computing environments where you can utilize clouds and different types of devices, segregation is something that's actually part of our modern world. So we can utilize that, and then we get the full flexibility of software with a very high level of security and providing additional features like key usage control, which I'll describe in a moment. Okay, so I'd like to now go through a few best practices or use cases. And the first is agility, which I've already discussed before recently. And the example I'm going to start with now is actually a real example that one of our customers, a first-tier financial institutions, has actually deployed. A very standard thing is that we have a business unit within our institution, within our organization, that wants to deploy some new service. And being the modern world that it is, we want to make sure that this deployment is as quick as possible, but it also needs to be secure. And this specific solution, you can think about the fact that it maybe requires user authentication to this solution, to the service, as well as encryption on the back end to protect the data or secrets that are being used. A very important goal, which really is at the core of agility, is the ability to be able to move the solution around at will. So we'll start by deploying on premises, but eventually we'd like to be able to migrate to the cloud, and we'd also like to not be locked to any specific cloud. Costs can change in different clouds. There may be different places around the world where different clouds are attractive. And we need to have that flexibility to move around. And so we have to somehow be able to deploy keys both at the end user on their device, whether it be their laptop or their mobile, on clouds in the data center, and have these keys be protected and deployed very, very quickly. So hardware-based solutions just don't work for this example. Again, they give us very good security, but they'll take us a long time to deploy. And in fact, it can take up to 9 months to deploy a new HSMs for our solution. It may be less, but it can go up to that amount of time. Providing hardware for the user is obviously something which is not going to be considered for most cases. So hardware doesn't help. Software-based solutions, pure software solutions, as we said, are not secure enough. And this is a classic example of where MPC can be a perfect fit because it has all of the agility and flexibility of software. You're not bound to any specific cloud or data center. You can work also, the same solution works for the endpoint and for the server side, and really giving exactly what you need in this specific case. Next, I want to talk about the whole bring your own device problem. This is a fact of our modern world. Users have their own phones. Most users are not willing to walk around with 2 phones, one for home and one for work. It's very hard to get strong isolation between the work part of the user's phone and the home part of the user's phone. There have been some attempts to do that, but they haven't really succeeded. And so either we have to compromise on security or compromise on usability. Are we going to just allow the user to store their secret authentication key on the phone and have it be stolen very easily, or are we going to require additional methods of step-up authentication and so on, which users tend to not like? So the aim is to try and get a high authentication assurance level, but with a software-only solution and without requiring step-up authentication. That's what we would really like. And again, this is a use case where hardware is just not relevant, and software-only solutions are not secure enough. How can we get 2-factor authentication on a mobile device which is inherently insecure? The answer is by not storing the key on the device at all, but storing only a share of the key on the device. If we have one share of key on the device and the other share in a server, then the key cannot be stolen from the device. One thing I didn't mention beforehand is that this sharing of the key actually is automatically changing all the time to make sure that the key material, no relevant key material, even a share of the key material, exists on the device at any time at all. Now, given that this is the case, that you can't steal the key from the device, this means that you actually have to hold the device physically in order to authenticate. So once I add a password on top of that, I now get 2-factor authentication on a mobile, which is something that I don't have otherwise. If I just use a software token, then I'm not getting that level of security that I need because it can be cloned. And if I want to try to use a secure enclave on the phone, so if it's a general trusted execution environment, we've talked about the problems with that. What about something like Touch ID on iPhones? That actually is done very, very well, but it's a very limited functionality. It only gives you one specific operation, which is ECDSA signing. It doesn't meet general needs. And with BYOD, I can't enforce everybody to have the latest iPhone with Touch ID built in. Actually, I have to support a broad range of different devices, and using MPC, I can actually get security across the board. And last, I want to talk about multi-layered security. As I mentioned in the beginning, there is no perfect security. MPC is not perfectly secure because if the attacker does eventually get to all the machines holding the shares of the secret, then it can be reconstructed. What we need to do is just make it very, very hard for the attacker. And that means we have to have multi-layered approaches to security. And one layer that we need to talk about, and we haven't really talked about until now, is that of authorizing key usage. There's one issue of protecting keys, and that is really the primary problem, because if a key is stolen, then it can be used without us ever knowing, and it can be used at a very rapid rate, and we have no control anymore about what's going on. But there are actually some use cases where even a single usage of the key is already a huge disaster. This can be for example, in an in-house CA, certificate authority, that if you can get a certificate signing key, then you can now generate certificates that everybody will accept. So even just getting one certificate like that is already very, very problematic. You can think about high-value transactions, a digital signature to transfer millions of dollars. You just need one signature to be generated like that, and you're in trouble. If you think about the crypto asset, the cryptocurrency world, it's much worse there, because their transactions are actually irreversible, and it's enough to just use the key once, and everything is lost. MPC actually provides the capability of setting up complex, advanced authorization structures and policies that are enforced cryptographically. So, for example, I could have two sets of approvers and require that at least 2 out of the 3 of the first set and at least 1 out of the 3 of the second set will approve the transaction before it can be carried out. And this is not by inputting a password, it's actually cryptographically enforced at the level of the generation of the signature using secure multi-party computation. And these approvers may be between the bank and the customer, or even there can be additional sets, and we can have a trustee, and we can define very general authorization policies that make it very hard to use the key even once. You obviously wouldn't do this for transactions that are happening all the time, but they make a lot of sense for very high value and critical transactions. So that's one issue that you should take into account when building a solution. MPC is suited for this, but it doesn't have to be the only solution. This type of thing could easily be incorporated into dedicated cryptographic hardware solutions. The HSM manufacturers haven't done it, but I would very much hope that they actually incorporate this, because that will provide an additional layer of security that is missing from that whole space. Another place where we have exactly the same issue, this can be deployed in different solutions, but it hasn't typically until now, is what to do when you do detect that there has been key misusage. And how do you detect that quickly and prevent it from continuing? And this can be done by incorporating security policies inside the mechanism that carries out the cryptographic operation. So, for example, we can be running anomaly detection on the device that carries out the cryptographic operations to check that these operations are not anomalous. That's number one. Number two, we can also do things like rate limiting by saying that you can only do a certain number of transactions per minute, and this can be the difference between a breach where 80 million credit card numbers are leaked versus 1,000. One makes it to the news, and the other doesn't, of course. Again, this could easily be incorporated into HSM and dedicated cryptographic hardware solutions, but it hasn't been, and making those changes is a big challenge, and something that due to the lack of agility of hardware solutions is something that I'm skeptical we'll see in the near future, but I do hope that the HSM manufacturers try to incorporate such solutions. Multi-party computation, because it's pure software, is very amenable to these types of solutions, and in fact, Unbound solution specifically does have this sort of capability built in. So in conclusion, the digital transformation that we're all familiar with and trying to adapt to requires us to work in a very different way than we used to. The standard solutions that we used to use and worked very well for us for the last 20 or so years just don't work anymore. Software-based solutions that may have been secure enough 10 years ago are not secure enough anymore, with modern attackers belong to large organized crime organizations. And hardware solutions that can provide a good level of security don't work in modern, virtualized, flexible computing environments. And the cost of failure in those devices is so high that, again, with the sophistication of attackers, we have to think about whether that's the route that we want to go for new solutions. There are a number of different directions that are being proposed, and different technologies and solutions available. There is not going to be any single solution which is good for everything. There are some secrets that do not need very, very strong protection. Maybe the threat to losing them is very mild, and it's okay to go with a software token. And there are some solutions where we're going to stick with hardware, A, because it's regulated, or B, because it's not something that requires the flexibility, and we know how to work in that way, and we're going to stay with that type of solution. But there are a lot of other problems and security issues that need to be solved that neither this pure software tokens solution or the hardware solution provides a reasonable way of working, and we can use things like multi-party computation in order to solve them. In the future, we'll hope that the trusted execution environments that are developed in the next decade will also provide good solutions that give us both flexibility and high security, but at the moment, they're not really a good enough option. Thank you very much.
Yehuda, thank you so much for your time today. We wanted to take the opportunity to answer some questions from the audience. So for the first question, can you share some information on crypto agility? And with that, what do you see as the biggest threats and how do you address them?
Yeah, sure. I guess when we talk about crypto agility, we talk about the ability to update or fix problems that arise. And there are two main threats that we need to deal with. One is a flaw that we have in our implementation, in our solution, a bug of some type. And we should always assume that such bugs exist, because that's the nature of software, of hardware. That's the nature of the beast. There are bugs, and we need to plan ahead and realize that with attackers becoming more and more sophisticated and with more and more resources, then any such bugs will eventually be found. As such, we have to build into any solution that we provide the ability to update and fix that bug, and then prevent attackers from, for example, rolling back newer versions to older supported versions where the bug still exists. That requires building the ability for a secure update into the solution at scratch. And it also means that we have to have a plan ahead of time about how we roll out such solutions, such fixes very, very quickly. Of course, with software-only solutions, this can be handled in a much faster and more effective way. But even if you're doing hardware, it's important to have such plans in place. The second area where we have to think about crypto agility is just the development of cryptographic knowledge. Sometimes new attacks on existing schemes are found that were not known beforehand. Hash functions have been broken. MD5 and SHA-1 were once considered secure hash functions and are now no longer considered secure, and we have to be able to swap them out. There is the threat of quantum computing that will force us to move over to post-quantum secure cryptography. I'm personally not concerned that that's going to be happening anytime soon. However, we do need to be ready for that eventuality, just in case it does happen. NIST is now running a competition to have post-quantum secure cryptography. And it's just really, at this stage, I think, a reminder that any cryptographic solutions we put out there have to, any software we put out there, any solution we put out there has to have built in the ability to swap out cryptographic primitives with new ones that are still secure given whatever the current threat landscape is.
Great, thank you for that. You talk a lot about MPC. How does MPC compare to secret sharing?
So secret sharing is a tool that we use inside MPC, and secret sharing talks about how we can take any secret value and split it into different pieces so that no subset of the pieces of a specific size, what we call the threshold, reveals any information about the secret itself. In the context of what we discussed today, I can use secret sharing to take a key and split it to, say, 10 different parties. machines, devices, end users, whatever, and only some subset that I define, like 4 or 6 or whatever I want it to be, will be able to reproduce the key, and any smaller subset won't know anything at all about it. As such, secret sharing is a good starting point for MPC. But if I just use secret sharing, then when I want to actually use the key to decrypt or sign or whatever it is, I have to bring all the pieces together in order to reconstruct the key. And then once the key is reconstructed, I can go ahead and actually carry out the computation. The problem is that that means that the entire key is in memory at one point in time, in which case it can be stolen. We have APTs that can sit for a long time on a device that eventually is supposed to reconstruct the key, and then we've lost everything. MPC can take secret sharing as a starting point, but can then do the computation without ever bringing the pieces together. So you actually have to breach, the attacker actually has to breach all the machines that have those shares, whatever the threshold may be, essentially at the same time in order to learn anything about the key itself.
And for the final question, what is the performance of the MPC approach?
In general, that's a hard question, and it depends specifically on what we're computing with MPC. So there are problems that are more amenable to MPC and can be solved very efficiently, and there are problems that are more difficult to solve in MPC. Today we've discussed using MPC to protect keys, so for signing, decryption, symmetric, asymmetric, and all of those sort of tasks. We have very, very good MPC solutions in place today. And the performance that you get is comparable to that of what you would find in modern HSMs. In terms of throughput, the advantage of MPC is that you can simply add more software components and then linearly increase the throughput of the solution, and that's one of its big performance advantages.
Thank you again, Yehuda, for your time today. If you have any questions about the information presented in the webinar, please contact us at the link you see on the screen. Thank you.